Mastering deep learning. Deep learning models implode without regularization. Why are regularization techniques, such as dropout and L1/XYZ regularization, essential in deep learning to prevent overfitting and improve the generalization capabilities of neural networks? Deep learning models, particularly neural networks, are prone to overfitting due to their immense capacity to learn complex patterns in data. Overfitting occurs when a model is too complex and learns the noise in the training data, rather than the underlying patterns, resulting in poor performance on unseen data. Regularization techniques, such as dropout and L1/XYZ regularization, are essential in deep learning to prevent overfitting and improve the generalization capabilities of neural networks. Overfitting arises from the model's tendency to fit the training data too closely, resulting in poor performance on new, unseen data. This happens when the model is too complex, having more parameters than necessary to capture the underlying patterns in the data. As a result, the model becomes specialized to the training data and fails to generalize well to new data. Overfitting can be identified by observing the performance of the model on the training and validation datasets. If the model performs well on the training dataset but poorly on the validation dataset, it is likely to be overfitting. Dropout, a popular regularization technique, addresses overfitting by randomly dropping out neurons during training, effectively creating an ensemble of different models. Each epoch, a random subset of neurons is randomly selected and ignored during training, which prevents the model from relying too heavily on any single neuron. This randomly generated ensemble of models improves the model's ability to generalize to new data, as it is forced to learn multiple representations of the data. Another essential regularization technique is L1 regularization, also known as LASSO, least absolute shrinkage and selection operator, regression. L1 regularization adds a term to the loss function, proportional to the absolute value of the model's parameters. This term, known as the regularization term, forces the model to have smaller weights, which in turn reduces overfitting. The L1 regularization term has the effect of setting some of the model's parameters to zero, effectively reducing the model's capacity and preventing overfitting. XYZ regularization, also known as ridge regression, is another regularization technique that adds a term to the loss function, proportional to the squared value of the model's parameters. This term, similar to L1 regularization, reduces overfitting by forcing the model to have smaller weights. XYZ regularization, however, does not set parameters to zero, unlike L1 regularization. Instead, it reduces the magnitude of the weights, smoothing the optimization process. These regularization techniques are essential in deep learning to prevent overfitting and improve the generalization capabilities of neural networks. Without regularization, neural networks tend to overfit the training data, resulting in poor performance on new, unseen data. By incorporating dropout and L1/XYZ regularization, the model is forced to learn more generalizable representations of the data, improving its ability to perform well on new data. In addition to improving generalization capabilities, regularization techniques also provide several other benefits. They increase the robustness of the model to input perturbations and reduce the risk of overfitting to the noise in the data. Regularization also helps to reduce the risk of exploding gradients during training, which can cause the model to diverge or converge to a poor local minimum. In conclusion, regularization techniques, such as dropout and L1/XYZ regularization, are essential in deep learning to prevent overfitting and improve the generalization capabilities of neural networks. By incorporating these techniques, the model is forced to learn more generalizable representations of the data, resulting in improved performance on new, unseen data. As deep learning models continue to grow in size and complexity, the importance of regularization will only continue to grow, ensuring that models generalize well and provide accurate predictions on new data.